Good afternoon. Let us start our lecture today. So today we're going to learn something new, which is the stem-living theory. Basically, in the previous class, we learned the way to compute eigenvalues and how to solve equation, but we didn't know where they come from. And today we're going to learn the main theory. Basically, what we did in the previous class belongs to the so-called stem-living theory. And the stem-living theory is written as follows. Stem-living theory. Right. So the stem-living theory says the following. So given a function u x, and define the operator all right. L of u is d over dx of dx du over dx plus qx u, where p, x, and qx are function. Right. So in the stem-living theory, I give you a function u. Now I define the operator d over dx of p, u over dx plus qx u, in which q and u are functions. All right. So this is the general form of the operator. Example. So in the case of p, x is 1 and qx is 0. What do I get? Let me explain again. So you have a function u, right? So you define the operator or the action on u as follows. You take the first derivative in x, you multiply this with a function p, and you take again the derivative in x. P is given, and then you add everything with q, x, right? So this is the stem-living operator. Now let us consider the special case where p is 1 and q is 0. What is the form of the stem-living operator? Yes?
LW equals u delta prime?
Yes. Can you sign the back of the paper, please? So in this case, LU will be u second, right? So this is what is the name of this operator? Laplace operator, right? So this is the Laplace operator. All right. So so now I have another example, which is the following. So I have example. I have FU. I have FU is x squared u second plus x u prime plus 2u. So you write L in the stem-living form. All right. So now I have this operator. I have to write under the form of the stem-living. So how can I write it? Right, so this is straightforward, right? So in the first case, LU is u second because so in the case that LU is u second, P is 1 and Q is 0. Now suppose that I have this complicated form, but I said that I can write this under this form. So how can I do it? I want to find P and Q, right? We have to find P and Q such that we have to find P and Q such that we can write x second u second plus x u prime plus 2u is p u prime prime plus q u. Right? This is a form of L, x squared u second plus x u prime plus 2x, right? Now I want to write like in the Sturm-Liouville operator. What I do is that I'm going to find P and Q such that this guy can be written under this form, right? So this is nothing but Pu prime plus Qu. We're gonna try to find PQ such that this can be written under this form. So do you have any idea how I can write it this way? Yes?
We can assume that Q is equal to 2, right?
Q is equal to 2. Yes, and P.
I'm sorry?
And P.
We're going to have to do some derivation on that, but I would assume 3 x cubed over 3.
This is a good idea. Can you sign the back of paper, please? And you? Yes?
Yeah, I was just saying you could integrate backwards to find P and Q.
Right, so you just do it backward, right? So you just expand this and you identify the coefficient on both sides. Can you sign the back of the paper, please? So to do this, you do it backward, right? So you have P prime, U prime, prime P plus Q is P prime U second plus P prime U prime, plus Q. What you do is you expand this guy and you make the coefficient of this guy to be equal to this guy. Alright? You do it backward. I explain again. You want, this is a normal operator, a normal form, differential form. You want to write under the form of the Sturm-Liouville. Then you have to find P and Q such that this can be expressed under the form of the Sturm-Liouville, right? In order to do that, you just do it backward. You expand this and you have P U second plus P prime U prime plus QU. Alright? It's clear? Now we identify the coefficient, right? So this gives you x squared u prime prime plus this is p prime x u prime plus 2u. Right? So how can I choose P and Q? There's a little yes.
So like P would just be x squared and the Q would be 2, like you say.
Yes. Can you sign the back of paper, please? So I think I missed it too. Right. So now you're gonna identify this guy with this guy and this guy. All right. I missed it too. So now you identify things and you have what? You have P. So identifying the coefficient of u second, u prime, and u, we get P is x squared, P prime is 2x, and Q is 2, right? Right, so you just identify, and you found that P is x squared, P prime is 2x, and Q is just 2. Right. So now you replace everything here. You're gonna have x squared u second plus 2x u prime plus 2u, and this is equal to x squared u prime plus 2u. All right. So, right, so basically this is the form that we are going to study. In the previous example, the Laplace operator corresponds to the special case of P is 1 and Q is 0. And then, for instance, this one, x squared u second plus 2x, u prime plus 2. What you do is that, okay, you identify the coefficient PQ with the coefficient of this equation, right? So you expand this term, you get P prime and Q. And then you make them equal to x squared, 2x, and 2, right, like this. And you find that P is x squared and Q is 2, right? And so then you can write it under Sturm-Liouville form. Yes?
In this case, it looks like Q is P double prime. Will that always be the case?
No. For instance, I can write, for instance, okay, so here I can put 5, okay? Here I can put 5, then I can have 5 here and have 5 here. So it doesn't matter, right? So Q is not always. So Q is the easiest guy because this is the 0, the term associated to the u without the derivative, right? So, all right. So basically, this is the operator complicated form that we have. The special case of this was what we studied in the previous class. We did a lot of exercises on this, but basically, the previous classes are just special cases of this theory. All right. So today I'm gonna show you some of the theorem by Sturm-Liouville, and that explain why in the previous class you can expand and you can do eigenvalue and eigenfunctions. All right. Right, so consider the equation, the following equation. On AB. All right, so you're going to have L of phi, which is phi second Q P prime plus Q times phi is lambda phi, right? On AB with the boundary condition. You have A phi prime at A plus B, phi, no, it's not A, B, C1 and C2, phi at B is equal to 0, right? C3 phi prime at B plus C4 phi prime at B is 0, right? So this is the eigenvalue problem that we study, right? So we want to find phi and lambda. Let's satisfy this equation with this boundary condition. All right. So we want to find. We have to find. No, this is unknown. Unknowns. Phi and lambda, and given P, Q, C1, C2, C3, C4, and interval all right. So this is the abstract form of the equation that we have. So you're gonna have P phi prime plus Q phi is lambda phi, and this is solved on AB. right? You have a boundary condition at the point A and the boundary condition at the point B. The boundary condition at the point A and the point B have those forms, right? And so basically, you solve for phi and lambda. PQ are coefficient. C1, C2, C3, C4, they're constant, and interval is given. All right? This is the so-called Sturm-Liouville eigenvalue. Liouville eigenvalue problem. All right? So some of the special cases. Special cases. So in 2.3.5 we have phi xx plus lambda phi is 0 minus phi at 0 is 0 and phi at 2 is also 0. So in this case, what is P, Q, C1, C2, C3, C4? I is 1. All right. So in one of the previous examples, we consider this eigenvalue problem. This is 2.345. The second derivative of U is lambda. Phi 0 is 0. Phi 2 is 0. And then PQ, C1, C2, C3, C4 can be deduced from this general form. So what yes?
How come the fees on C3 and C4 are both prime, but...
Thank you. Can you sign the back of the paper, please? So what is the value of A and B in this case? Yes?
A is 0, B is 2.
Yes. Can you sign the back of the paper, please? So A is 0, B is 2. What are P and Q in this case? Yes?
Is P1 and Q0?
Yes. Can you sign the back of the paper, please? So P in this case 1 and Q is also 0. All right? Now, what are the values of C1, C2, C3, C4? Yes?
C1 and C3 are 0, and then C2 and C4 are 1.
Yes, can you sign the back of the paper, please? So in this case, C1 and C3 are 0, and C2 and C4 is also 1, right? Basically, the example that we considered in one of the previous class is a special case of this Sturm-Liouville eigenvalue problem. So in this Sturm-Liouville eigenvalue problem, you have a second order differential form of this function phi, right? P and Q are given, and the boundary condition has to be of this form, right? Right. So now let us try to see another example in the previous class.
Can you explain why P is 1 and Q is 0?
Okay, good. All right, so in this case, what? Can you sign the back of the paper, please? So in this case, right, so this is the general form. General form. And the special case is phi second is lambda phi. All right. The general form is PQ phi second prime P phi prime plus Q phi is lambda phi. And the special case phi second plus lambda phi, right, is equal to lambda phi, right? So here you have what? You have 0 phi, which means that the Q is 0, and here if you put 1 here, and this is phi second.
Okay, thank
Yes.
you.
No, I'm just putting my...
Right. Right. So now I have another example that we consider in the previous class. We have what? We have phi second is lambda phi. Phi at 0 is 0 and phi prime at 1 is 0. Alright, in this case, what are the values of A and B? Yes, can you say in the back of the paper, please? So A is 0 and B is 1, right? In the previous class, in 2.3.6, we consider phi second is lambda phi. So in this case, phi 0 is 0, phi prime at 1 is 0, alright? In this case, the domain is 0 and 1, right? So this is on 0, 1. So A is 0 and B is 1. What is the value of P and what is the value of Q? So P is 1 and 0. Can you say the back of the paper again, please? P is 1 and Q is 0. So what are the values of C1, C2, C3? Yes?
C1 and C4 are equal to 0, C2 and C3 are equal to 1.
Yes, can you say at the back of the paper, please? So C1 and is 0, C4 is 0, C2 and C3 they're 1. Alright, so all of the previous exercises that we did are special cases of this Sturm-Liouville eigenvalue problem. Alright, so far we've learned the so-called Sturm-Liouville eigenvalue problem, but I didn't say that this is Sturm-Liouville eigenvalue problem. So let us go to another example. So this is 3.5.7. Phi second is lambda phi on 0, 1. Phi of 0 is 0. And phi of 1 plus phi prime of 1 is going to be 0. Alright, so in this case, what are A and B?
1, 0.
1, 0. Can you say at the back of the paper, please? So A will be 0 and B will be 1. So what are P and Q? Yes?
1 and 0.
1 and 0. Can you say at the back of the paper, please? So P in this case 1 and Q is also 1. Right? So what are the value of C1, C2, C3, C4? Yes?
C1, C3, and C4 are 1, and then C2 is 0.
Yes, can you say at the back of the paper, please? So in this special case, C2 is 0, C1, C3, C4, they're all 1. Alright? So basically, our point is that this is 7. Alright, so our point here is that in the previous lectures we studied a special case of a more complex and more abstract form, which is the so-called Sturm-Liouville eigenvalue problem. Alright? Now, right, so properties of the Sturm-Liouville eigenvalue problem. Right? So the number 1, the equation 1 has infinitely many solutions. Alright, so lambda 1, phi 1, lambda 2, phi 2, lambda n, phi n. Right? And so you have what? You have P1 prime plus Q, P1 is lambda 1, P1 and then you have C1 P prime at A plus C2 P1 at A is 0, and then C3 P2 P1 prime at A plus P4 P1 at A is 0. And right? So property number 1. This problem has infinitely many solutions. You have lambda 1 phi1, lambda 2 phi2, lambda n phi n, right? So all of them satisfy this equation in the sense that you have p phi1 prime prime plus q phi1 is lambda 1 phi1, all right? And then you have the same boundary condition. That's clear? So, so in the special case of 2.3.5, in 2.3.5, you have what phi second, because lambda phi is 0 on 0, 2. Phi 2 is phi L, 0 is also 0. So the eigenvalue and the eigenfunction that we found phi n x is sinus of n pi x over 2, and the lambda n will be n pi over 2 squared, right? I explain again. For this problem, you have infinitely many solutions, right? You have lambda 1 phi 1, lambda 2 phi 2, lambda n phi n, and all of those satisfy the equation. For instance, you have p phi 1 prime plus q phi 1 is lambda 1 phi 1, and you also have the boundary condition, yes?
Is there a reason why we're always using A and never using B, like for C3 and C4?
Can you sign the back and paper, please? Right? There's a typo there. So this is B. Right? So in the so for those kind of eigenvalue problem, you have a series of solutions. Phi 1 lambda 1, phi 2 lambda 2, phi n lambda n, right? For instance, for this problem, you have phi n is sinus n pi x over 2, and lambda n is n pi over 2 squared minus. So we're going to check it. So for n is equal to 1, we show that this is satisfied. All right? So when for n is equal to 1, phi 1 of x will be sinus of pi x over 2, and lambda 1 will be minus of pi x over 2 squared. All right? Good. So in this case, this is equal. So in this case, you have what? You have p is 1 and q is 0, right? As in the previous discussion, we know that p is 1 and q is 0. So you're going to have 1 times phi 1 prime plus 0 phi 1. Right, so this is phi 1 second. Yes?
For lambda 1, where did the x come from? Isn't it lambda 1? Because I thought lambda is n pi.
Can you sign the back of the paper? This is the n of so this is 1. Yes. Right? So in the special case of 2.3.5, p is 1 and q is 0. So you have 1 phi 1 prime plus 0 phi 1 is phi 1 second, which is exactly the form that we have over there. Right? So now I'm going to compute phi 1 second to see that phi 1 second is lambda 1 phi 1. Right. So you have what? Phi 1 second is going to be sinus of pi x over 2 prime. This will give you pi over 2 cosinus of pi x over 2. And phi 1 second will be minus pi x pi over 2 squared sinus of n of pi x over 2. All right. So basically, this is lambda 1 phi 1. So this is lambda 1, and this is phi 1. It's clear? I explain again. The first thing that we have in this theory is that this equation has infinitely many solutions for lambda n and phi n. All right? We saw that already in 2.3.5. In this special case, p is 1 and q is 0. We know that phi n, computed from the previous lecture, that phi n is sinus of n pi x of L, and lambda n is minus n pi over 2 squared. Right? In this special case, p is 1 and q is 0. Now I'm going to check that this is definitely one solution for n is equal to 1, like what I drew over here. Right? So p is 1 and q is 0. So I have phi 1 second. Phi 1 prime will be the derivative of sinus. This is cosinus plus times the factor. And the second derivative will give you pi over 2 squared minus and times the phi 1. So basically you have phi 1 second is equal to lambda 1 phi 1, which is this equation here, or this equation here. All right? But there's one more thing that I want to check. What is it?
The boundary condition?
Boundary condition. Can you stand back up, please? So now I'm going to check the boundary condition, right? So I have to check this condition. So I want to know that phi 1 at 0 and phi 1 at 2, they are both 0. So, so I have phi 1 at 0 is sinus of pi times 0 over 2. This is 0. Phi 1 at 2 will be sinus of pi times 0 over 2. And this is sinus of pi. And this is also 0. Right. So which means that, okay, I have lambda 1 and phi 1, they are both solutions of this equation, and with the same boundary condition that we want in the beginning. It's clear? In this special case, as we computed in the previous class, we have a series of solutions, lambda n and phi n, and if you generalize it, like in the Sturm-Liouville eigenvalue problem, all of the you also have a series of solutions, lambda n and phi n. It's clear? Questions? Now let us go to the next property. This is property number 2. So B, the eigen values are real, countable, order, and there is, and in the following sense. You have minus 1, lambda 1 is smaller than minus lambda 2, and the limit when n tends to infinity of minus lambda n is going to be infinity. Right? So the second property is that all of the eigenvalues, lambda 1, lambda 2, lambda n, they are ordered in the following sense. The minus of lambda 1 is smaller than the minus of lambda 2, and this is smaller than the minus of lambda n. And if you take the limit of minus lambda n, it's going to be infinity. Can you see it in this special case? Yes?
Well, since we know lambda n is n pi over 2 squared, and the n term is on the numerator and the n approaches infinity, the whole term will reach infinity.
Yes, can you say the micropressure please? Right, so in this special case, what you have is the following. So in this case, you have lambda n, phi n is sinus of n pi. Lambda n is the minus of n pi over 2 squared, right? You're going to have lambda 1 will be minus pi over 2 squared. Lambda 2 will be minus 2 pi over 2 squared. And which means that minus 1 pi over square smaller than 2 pi over square n pi over 2 square. This means that minus 1 lambda smaller than minus 2 lambda smaller than minus lambda n, right? So in the previous example of 2.3.5, we know that lambda n is minus n pi over 2 square, right? Lambda 1 is minus pi over 2 square, lambda 2 is minus 2 pi over 2 square. So if you take the minus, this is smaller than this, and this is smaller than this, all right? Which means that minus lambda 1 is smaller than minus lambda 2, and this is smaller than minus lambda n, which is exactly what we see here. Questions? It's good. And so you have minus lambda n is going to be n pi over 2 square, and this is going to infinity when n is going to infinity. That's good. Questions? Explain it one more time. So for this problem, with under this form, right? You have an infinite number of solutions, lambda 1, lambda 2, lambda n, and phi 1, phi 2, phi n, right? But those lambda 1 and lambda 2, lambda n, they are not arbitrary, they are order. In the sense that minus of lambda 1 is smaller than minus of lambda 2, and is smaller than all of the order of lambda with the bigger index. And the minus of lambda n is going to infinity. You see that clearly in this example. You have lambda n is minus n pi over 2 square, and so which means that okay, all of the smaller index is smaller than all of the bigger index, and this is going to infinity. Questions? Right. So now the next property is the following. So numbers C. So all of the eigenfunctions are orthogonal with respect to a weight sigma x, say wx. So with respect to an inner product, with weight wx. Right, so you have the f and the g of x. W will be the integral from a to b of wx, fx, gx. So let us. All right. So so we're gonna say that okay, there is a weight Wx such that all of the eigenfunctions are orthogonal with respect to this inner product, right? So in the beginning, I think I forgot to mention to you that there is a W here, but let's discuss that a little bit later. Right. So let us go to this example, right? Let's go to this example. So we know that all of the phi n here, they are orthogonal, like in the previous example, right? So we know that phi n x are orthogonal. All right. So we know that all of the phi n x are orthogonal in the following sense. Integral from 0 to 2 of phi n of x, phi m of x, dx is 0. So this is something that we observed in the previous exercise. We know that all of the phi n and phi m are orthogonal because if you multiply n and m, n has to be different from m, right? And you integrate, they're gonna be orthogonal. And this, we call it an inner product, right? Inner product. So basically, you're gonna have f(x) and gx is going to be the integral from 0 to 2 of fx, gx, dx. I explain again. In the previous exercise, we know that all of the eigenfunctions that we found, they are orthogonal in the sense that if you multiply two of them, two different ones, right? So when you say orthogonal, you have to say that one function is orthogonal to a different function. You cannot say that one function is orthogonal to itself. So n has to be different from m, right? So in this sense, if you multiply these two functions and you integrate from 0 to 2, this integral is 0. When this integral is 0, I say that they are orthogonal because I define the inner product to be the integral from 0 to 2 of this product. All right? So in this case, so let me forget first about the inner product here, the weight. So in this case, you also have the same thing. All of the eigenfunctions that we found in the previous step, they're also orthogonal in the following sense. So we have phi n and phi m is going to be 0, which means that integral from a to b of phi n x, phi m x, dx is 0. All right? Right, so I wrote previously a w because I want to generalize this problem to something which is more complicated. Right, so now if I consider this problem with some w phi, right? So suppose that I give you another function w and I have to solve this equation. The same thing happens, except that here you have to put a weight. To illustrate that, let us consider this problem again. So suppose that we want to study this problem, but a little bit more difficult. Let's say x squared plus 1 phi x. Right, so this is the w that I put into the equation. Confusing? No? So, now what I'm trying to do is I try to make this problem a little bit harder. I'm going to put a w here, which is a weight. Coming back to this equation, this eigenvalue problem, what we want to find is a function phi such that the second derivative of this function is lambda times phi multiplied with another function x squared plus 1. This is more difficult, right? So in the previous one, you don't have this. You have all of the sinus and cosinus. But now you have this way, right? Then you're going to have phi 2 is going to be phi 0, and it's 0. So in this case, we also have a series of solutions. A lot of solution. Lambda 1, phi 1, lambda n, phi n. They are also orthogonal. So they also, you have phi 1. Second is lambda n, x squared plus 1, phi n. And then phi 0 is equal to phi 2. And this is also 0. And then you also have phi n x times phi m x. It will go from 0 to 2. X squared plus 1 dx is equal to 0. Right? Be careful because here I just put a new weight which makes the problem more complicated and it's confusing. I explain again. In the previous example, if you don't have a weight here, which is the problem that we consider in the previous class, right? You have a series of solutions where there is no this guy, all right? So they are orthogonal. But now if I put a x squared plus 1, you also have a series of solutions, and they are also orthogonal according to this law, right? Questions? Yes?
Before we said that there were infinitely many solutions, are there infinitely many solutions here?
This is exactly the same. You have infinitely many solutions, lambda 1, lambda 2, lambda n, phi n. In this case, the theory is also applicable if I multiply this by lambda. So I change the equation. The solution will be different, but they also satisfy the same property, except that when you say that they are orthogonal, you have to multiply with this x squared plus 1, right? So now, for this problem, C tilde. For the problem with the weight. With the weight W tilde. All of the eigenfunctions are orthogonal with respect to the following inner product. So we have interval from 0 to A to B of W x, phi n of x, phi m of x, dx is 0. Right? Questions? It's clear? Right? So if W is 1, this becomes the classical inner product. But now if I put a W here, then they are also orthogonal, but you have to put a weight into the inner product. Questions? There's no confusion when I pass from without W to with W. Stop me if you don't understand. Right? So, all right. So let us try to solve the following problem so that you see what is going on, right? So these are the three things that we study. Right. So, example. Now let us consider this Sturm-Liouville equation. You have x, phi prime prime plus 2 over x of phi is minus lambda sigma of x and then the boundary condition will be phi prime at 1 is 0 and phi prime at 2 is going to be 0. Right. So now we have a pretty complicated eigenvalue problem. Right? So can you tell me what is the value of P and Q? Yes?
P is x and Q is 2 over x.
Yes, can you sign the back of paper, please? So in this case, P is x, right? And Q is 2 over x. 1, 2. So what are the value of A and B? Yes? Yes, can you sign the back of paper, please? So A is 1 and B is 2. What is the W? Yes?
X to the negative 1.
Yes, can you sign the back of paper, please? So x to the negative 1. Right? And what are C1, C2, C3, C4? Yes?
C1 and C3 are 1, and then C2 and C4 are 0.
Right. Can you sign the back of paper, please? C1 and C3 are 1, and C2 and C4 are 0. Right? Questions? Right. So now let us try to solve this equation. Right. So now I'm gonna try to solve this equation, right? The first step I want to do is I want to develop this. Right. So you're gonna have what? You're gonna have x phi prime plus 2 over x phi is lambda 1 over x phi, right? What is the, when I expand this guy, what is this derivative? Yes?
X phi double prime plus phi prime.
Yes, can you sign the back of the paper, please? So you're gonna have x phi second plus phi prime plus 2 over x phi, and this is lambda over x phi. All right? Questions? It's good. Right. So now I'm gonna multiply this x over there. I have x squared phi second plus x phi prime plus 2 phi is lambda phi. All right? Yes?
What did you do with the 2 on top of the 2 over x again on the other side?
I just multiply x here. So I multiply x here and I multiply x here, and then 2 over x multiplies of x. Okay, so I'm gonna be slower. I multiply everything with x.
What about the step before that, like how it's lambda 2 over x phi? Where did the 2 over the x go?
That's a 1.
That's a 1.
Oh,
So 2 over the what?
The first line.
So the first line, right? So this, so I'm gonna do x phi prime, right? Will be x phi prime plus x prime phi prime, right? This is possible.
I just
So
got it wrong.
then this is x phi second plus phi prime. All right? Good. Right. So now I multiply everything with x, and I have 2 phi, and this is lambda phi. All right? So let me, so 2x plus x over x. Okay, so you have x squared phi second plus x phi prime plus 2 phi is lambda phi. All right? Good. Questions? All right. So, so how do you solve this equation? So basically for this equation, you're going to have the characteristic equation. Which is r squared plus lambda plus 2 minus lambda plus 2 is 0. Right. So this is the Riccati equation. And so you can check the book of Habermas about this characteristic equation. After you check, if you don't remember, the next class I can make a review class on this for you. Right. So you just check the book of Habermas of the previous class. So, all right. So in the case that you don't remember how to derive the characteristic equation, I'm gonna do it in the next class for you. So for now, if you don't remember, it doesn't matter. You just accept this form. It's clear? And then if there's problem, I'm gonna explain again how to get to this point, right? Right. So now for this one, of course, you also consider 3 cases. But like in the previous problem, 2 of them will not give you anything. So I'm gonna drop that 2 cases, and I'm gonna consider only the last case number 3. Lambda plus 2 is also bigger than 0. So in this case, you're gonna have a solution of the form C1 cosinus square root of minus lambda plus 2 log of x plus C2 sinus of square root minus lambda plus 2 log of x. Alright? So again, from here to here, you use something like the characteristic equation, like in the previous example. So you can check the book of Habermas. In the case that you don't remember that, I'm gonna go back and show you how to derive this equation. But for now, in the case that you don't, if you remember it, it's very good. If you don't remember it, you just take this characteristic equation, right? It's clear? Right. So now, in the case that you don't have, in the previous, like in the previous classes, you also have 3 cases. The 2 previous cases are trivial. So let me just focus on the last case where you have cosinus and sinus. So this is exactly like in the previous example, in the previous exercises. So you also have sinus and cosinus with the square root of 2 minus lambda, except that here you have logs, right? But this is the formula of this solution. And again, if you don't, if you go back to that book and in the previous class, and if you don't remember that one, if you don't feel comfortable, I'm happy to explain it to you again. But let us focus on this case. All right. So now suppose that you are in case 3, 2 minus lambda is positive, and you have phi x is going to be C1 2 minus lambda log x and plus C2 sinus of 2 minus lambda log x, right? So what is the next step? Yes?
We need to take the derivative of it.
Yes, and then you check the boundary condition, right? Can you sign the bind of paper, please? Right, so let us try to take the derivative of this guy. So the first one gives me C1 square root of 2 minus lambda minus sinus of square root of 2 minus lambda of x 1 over x. Alright, plus C2 square root of 2 minus lambda cosinus of square root of 2 minus lambda log x 1 over x. Right, so now I'm gonna apply the phi prime of 1 is 0. Questions? I explain again. So here you also consider 3 cases, but the first 2 cases are trivial and we don't have eigenvalue and eigenfunction. So let us suppose that we are already in case 3. So the phi x will have this form. So what I do is I take the derivative of this guy. I'm gonna get minus c1 square root of 2 minus lambda sinus of this guy times 1 over x, right? So this is the chain rule. The first derivative is the derivative of cosinus. So the derivative of cosinus is minus sinus. So this is why I have a minus, and I have a factor here, right? And 1 over x is the derivative of log. Question on that? It's good. So now for the second one, I'm going to take the derivative of sinus. So the derivative of sinus is cosinus. I have to remember that I have a factor here, so I have to put outside 2 minus lambda, and the log of x derivative will give me 1 over x. Questions? Yes? It's good. Now, I'm going to use the first boundary condition, right? So phi prime and 1 is 0. Is it difficult? It's good. Questions? So now you have phi prime at 1 is 0, which give me c1 of square root 2 minus lambda, sinus of square root 2 minus lambda, log of 1 over 1, plus c2 square root 2 minus lambda, cosinus of square root 2 minus lambda log 1 over 1, and this is 0. So what is the conclusion of this case? Yes?
C2 is 0.
Yes, C2 is 0, right? Can you send back the paper, please? So this is 0. Log of 1 is 0. This is 0. So log of 1 is 0, which means the sinus of 1 is 0, right? So I have C1 times 0 plus C2 times 1 is 0, which means that C2 is 0, right? Now I have phi x, phi prime of x, because C2 is 0, so phi prime of x will become minus C1 square root of 2 minus lambda sinus of square root of 2 minus lambda log of x 1 over x, right? So after replacing the first boundary condition, I get C2 is 0, which means that phi prime of x is minus C1 square root of 2 minus lambda sinus this guy over 1 over x, right? So what is next? Yes?
What are the other boundary conditions?
Yes, can you send it back to paper, please? So I'm gonna plug the outer boundary condition. So phi prime at 2 is 0, which means that minus C1 square root of 2 minus lambda sinus of square root of 2 minus lambda times log of 2 1/2 is going to be 0, right? But lambda is bigger, smaller than 2, so which means that you have sinus of square root minus lambda times log 2 is 0. Right? So what is the value of lambda? You have sinus of something is 0. What is this something? Yes?
So the entire term has to equal some factorial of n pi, right, in this case, because it has to equal 0.
Yes, so this is n pi. Can you send it back to paper, please? So here you're going to have 2 minus lambda. Log 2 will be n pi. All right? So 2 minus lambda square root log 2 is n pi, right? So you have 2 minus lambda is n pi over log 2, and 2 minus lambda is n pi squared over log 2 squared, right? So which means that lambda is 2 minus n pi over log 2 squared. Questions? Good. I explain again. Okay, so we have 3 cases. The first 2 cases are trivial, so the last case we will give you this kind of thing. You plug in the first boundary condition, you found that C2 is 0. You plug the second boundary condition, you obtain the sinus of square root of 2 minus lambda log 2 is 0, which means that square root of 2 minus lambda log 2 is n pi. which means that lambda has to be 2 minus n pi over log 2 squared, right? So what is, so this is the phi n and this is lambda n. Phi n, what is the value of phi n? What is phi n? Yes?
It's gonna be sine of, it's just gonna be the
C2 is 0.
sine term from what we solved
No,
earlier.
no, C2 is 0.
Oh, C2 is 0, so it'll be cosine term then.
Right. Can you send it back to paper, please? So, because C2 terms is 0, right? C2 is 0. We show it here. So the length over is just a cosinus term, right? So this gives you cosinus of minus square root of lambda and plus 2 log of x. And this gives me cosinus of n pi over log 2 log x. This is Pnx, right? Right, so I did it correctly. Right, so questions on this? Yes?
Where's the natural log coming from?
The log here.
Like, why is that there?
This is because you are solving the characteristic equation, right? So you have a Riccati equation, you go, so this is, so remember that there's the difference between this equation and the previous equation. This equation, you have variable coefficient for this equation. So you also do the method of characteristic, but because it's variational, you have a log coming out, right? So it's different from the previous exercises when you have a second order differential equation with constant coefficient, right? So this is something that you can find in the book of Haberman and in 3.1.1.3. But in the case that you don't really, when you go back to that book and you don't understand it, I can do it in the next class, right? So this is a little bit more difficult because you have log instead of x. The reason is because the equation has an x in the coefficient, right? So in the case that you don't feel comfortable, I can review this in the next class, all right? So for now, suppose that we have this form of the solution and suppose that you remember the form of this type, all right? So you plug everything inside, you have this phi n, all right? So this is basically the phi n and the lambda n. All right. So we say that they are orthogonal with a weight. What is the meaning? So in C theta, we said that phi n are orthogonal. In the weighted in the product. So what is the weighted inner product in this case? Yes?
So, this is more of a question. So we're just assuming that in this case it's like f, like you said previously, like f of x, g of x, and w of x, the integral from the a to b to b0.
Yes. Yes.
Oh, okay.
Yes. So in this case, because I put a w, so inner product is changing, right? So what is the inner product in this case? From the form, sorry, I erased the form, right? So the form we had from the beginning was this. This is the form. Right, so in this form you have what? You have P u sec u prime prime plus Q, U is W lambda times W times U on AB plus boundary condition. So in C theory, we said that phi and phi m are orthogonal with a new inner product. What is this new inner product? Yes?
Integral from 0 to 2 of x negative 1 times cosine of n pi over ln 2 ln of absolute value of x times cosine of n pi over 2 over ln 2 times ln of absolute value of x.
Yes, can you stand back the paper, please? So this inner product is the following: a to b, phi n x, phi m x, wx, dx is going to be 0. So this is the Sturm-Liouville theory. Of course, I just listed the property and I don't prove it because the proof is heavy, right? So you just know how to use it, and this is already good. So the difference is that in the previous lectures, w is 1. This is why the inner product is here, w has to be 1, right? So in this case, w is, what is w?
X over 1 over x.
1 over x, yes. So in this case, w is 1 over x, which means that you have what? You have the interval from 1 to 2 of phi n of x, phi m of x times 1 over x dx is going to be 0, right? So the different things that we have is 1 over x. And then you have 1 to 2 of cosinus of n pi x over log 2 of log x times sinus of m pi over log 2 of log x, right, times 1 over x dx, right? So in this class, we have a lot of things that are different. The first thing is that you have this p, which is not 1, right? And then you have another q. And the most important thing is that you have a w, right? So when the w appear on this side, you still have a series of eigenfunction and eigenvalue. They are also orthogonal, but the weight is 1 over x, right? When you multiply phi n and phi m, you have to multiply with 1 over x, and when you integrate everything, it's going to be 0. So this is the key difference. This is the key difference. Any questions? This is harder than the previous one, yes?
So where did you get phi n in this case? Because I know we got phi n from solving case 3 in the boundary.
This is phi n, and this is also phi n. This is, the phi n means that you replace 1, right? And then you, this is, I have phi 5, which is this one. But I said that they are orthogonal, which means that if I replace by 5 and 5, 5 and 6, and I integrate, they have to be orthogonal. So I just replace here 5 and 6, or anything that I want. Then the interval has to be 0, right? Other questions? Skip, yes?
Why is it using sine with BN?
Can you sign the back of paper, please? So yes, this is cosinus. All right. Right. So yes, there was a mistake. Right. So so the n and the m are just indexed, right? So you're gonna have a series of solution cosinus of pi over log 2 log x and 2 pi over log 2 log x. And if you put 2 of them together, you multiply, and of course you have to put this w, then they are orthogonal. Good? Questions? Right, so in this theory, in the Sturm-Liouville theory, this is very complicated because of the p, the q, and the w. But this is basically the same with the previous lectures. Sorry?
You solve the integration by parts?
I solve it. Yes, I don't prove it, right? So I don't prove it. I just told you that this is 0, but I don't prove it. This is, but you can prove it. But of course I don't prove it, right? So this is a lot of, this is the theory. So when you compute phi n and phi m, in the theory, we can prove that they are orthogonal. This can be proved, but you can use this result without proving, right? So here, you know that they are orthogonal, so this interval has to be 0. You don't have to prove it, because the proof will be a lot of work, right? Right. So this is given without proving. We can prove it, but in this case, I don't want to prove it. In general, if you are able to compute phi n and phi m, they will be orthogonal with respect to this W. Right? Anything that you found, that will be orthogonal. Questions? Good. Right. So now, the next thing that I want to So the next thing, which is the most important thing, the set phi n can be used as a basis for any continuous function f, right? So this can be used as a basis for any continuous function f. This function don't need to be periodic, right? So you have phi of x is going to be a1 phi1 plus an phi n of x, right? And an is going to be the inner product of phi f with phi n dividing by phi n. Remember that we have a w, so basically this is integral from a to b, fx phi nx dx dividing by a b phi nx. Then there's the w. That's good. So one very interesting of the Sturm-Liouville eigen functions are that you can use them as a basis to represent any continuous function. So if f is a continuous function, you can expand it on this basis, right? a1 phi1 plus an phi n. And of course, the an is the inner product of f with phi n dividing by phi n. You don't, so in the case that you have the w, you have to multiply with the w. So if w is 1, you don't have to multiply with w, right? Or when you multiply with w, which is 1, you get the classical result, right? So in other words, phi n the Sturm-Liouville eigenfunction can be used as a replacement for Fourier series. All right. So basically, when you solve all of these equations, you can find a list of solutions. All of those solutions are ordered, and they can be used as a basis to replace the Fourier series, right? So Fourier series is one special case, as I mentioned before, is one special case of the Sturm-Liouville eigenfunctions. And Fourier series belong to the bigger class of basis, which is called the Sturm-Liouville eigenfunctions. Questions?